Hey guys, back with another video, power converter after a long time. So as you can see, it's the boost converter, but the boost converter is already done if you have seen my earlier videos, and of course it was open loop. So now we're going to be doing the much more complex but more useful version, a closed loop one. So I did the closed loop buck converter a while back, and that was nice. I did that on the MSP 430 microcontroller. So now we're going to be doing the boost. As you can see, we have the input inductor, our low side switch, diode, and load, and of course a output capacitor here. It's not shown here in this image, but yeah, it's definitely there. So yeah, and today we're going to be, of course, closed loop, so we need to regulate the output voltage, right? We're not going to be varying it with a potentiometer, the duty cycle, right? How we were doing it in open loop. So we're going to be using a ADC inside of a microcontroller, of course. So today I'm not going to be using the MSP. I'll be using a new microcontroller, the STM. This is very popular, the STM32, in any kind of power application. Alongside this STM32 and the TI C2000, these two are very widely used in the power electronics industry for any kind of power converter. So it's nice because generally, and the one which I'm using, STM32F446RE, this is from the STM32F4 series. It has a decent amount of flash RAM, a lot of much more. It's like a, you could say it's like a bulkier version, like a bulked up version of the MSP. Everything is, in surplus over here, especially even if you just look at the clock, right? It's up to 180 megahertz, which is much faster. Our MSP was just 16 megahertz, so this is like a much beefier version of it. And there are many timers, unlike the MSP where we had just two timers. If I just go down here inside this data sheet to the timer, you can see here how many timers are there, and that's one of the specialities of STM. They have a timer for every single application. So you can see here these two, generally the 1 and 8 are they call the advanced control ones. The speciality of them is they have complementary outputs, and this is very important when you want to do any kind of inverter, or basically any kind of half bridge full bridge configuration, right, where you have the top and bottom MOSFETs. So you need dead time. So normally you would have to code that yourself in software, and it gets a little complex and not very reliable. But these advanced control ones, basically they have a dead time register where you can manually enter how much dead time you want, and it's, since everything is in hardware, it's very precise. So it's very nice, this timer. And soon I'll probably, my next video or one of the upcoming videos will be on this, using one of these advanced control registers. So stay tuned for that. But for now, the general purpose ones are good. They are used for normal, any kind of PWM, counting, anything. And these basic ones, basically they don't have a output channel, so basically you can't generate any kind of PWM or anything from this, since they don't have the capture compare channel. These are basically just used for generating, interrupts or any kind of fixed delays, but you don't want to use a software delay since it blocks the CPU and all. So we're going to be using this basic and general purpose today, two timers. So I'll just go into the, and of course the ADC. If I, let me just go down here and show you the ADC of it. If I just search, uh, yes, over here. So probably it'll be written somewhere down here. uh, yeah, here you can see here, that's the, it has a 12-bit ADC, which is very nice. Again, our MSP had a 10-bit ADC, so this is 12-bit, so it gives us a digital value of 0 to 4095, and there are many channels. We just need one today, but nevertheless. So let's just go into the IDE here. For the MSP we had the Code Composer Studio, and the STM, it has its own, the Cube IDE, and it has two things basically. This is the IDE itself, and also there is another part in this which is basically called CubeMX. This is like a visual version of it, and this is very useful. This is one of the big reasons why I switched over to the STM for this application, because manually writing all the bare metal code gets a little tough. Of course, you can do it, no problem, and they still do it. But this is nice because it has this visual kind of ID, you could say, where you can just pick the pins which you want. So, for example, here I chose which PWM pin I wanted, this one. So, if I click on it, it shows me what all alternate functions and all are there. So, it's very useful. Since I wanted it to generate PWM on this third timer, I used it for that. And let's say you want to set up the timer, right? Just go over here to this, it lists all the timers, and if you can just refer the same data sheet and get to know what timer is for what. So let's say you want to set up timer 3, right, like I did. You can choose on which channel you want it, select the auto reload register, which is basically how much what your timer will count up to, and then this mode, the this pulse value, which is basically your duty cycle. You can set all of it, and after you're done, if you just press the save button, Control S, it basically generates the code for you. You don't have to write it yourself. So that's a very nice feature of this. So if I just go into the main.c code which it has generated, you can see the MSP we wrote it by ourselves, right? The entire main.c code. But here you can see it generated all of the code, and it's very big. So that's why it's not really, nobody really, a lot of it is just comments, but still, that's why nobody really writes this. You can generate it. So just getting into the code now that we have a general background. What I have here is a lot of preprocessor directives, the hashtag define ones. They are basically much better. If you want to store a fixed value, they're very nice and you don't want to change this. So we have here, this is sort of like a function. This is basically because our output voltage which was there, if across the load, right, which will be there, that will be much higher. Let's say you want something like, today I'm going to be doing, the input is going to be 12 volts standard, and the output we are going to be trying 2-3 voltages, maybe 2 voltages. So but definitely high voltages, something like about 20 volts. So you can't directly feed that to your ADC, right? ADCs generally have a very narrow voltage level, and since this is a 3.3 volt microcontroller, same as the MSP, you can give maximum 3.3. So anything above 5, or most of the pins are 5 volt tolerant, so even up to 5 nothing will happen, but above that it starts getting dangerous because you do any kind of over voltage and there's no way you're giving 20 volts directly, it'll just fry the pin. So of course you have to use a resistor divider or something like that and scale down the voltage, and then inside your microcontroller you can use your voltage divider formulas, your ADC formulas, and bring back the analog voltage which is actually there in your power converter. So that's exactly what's going on here. I'm just multiplying it with the reference, the resistor divider ratio, and so this is our maximum digital output. We have to get that. So this will basically give us our analog voltage. And first off, let's, from the 12 volts, let's try and get 24 volts as our closed loop voltage. If it was a open loop converter, you would manually, calculate the duty cycle, put it in the capture compare register, and just flash it onto the code, and yeah, you would get 24 volts, no doubt. But here we're not doing any of that. It's going to measure the voltage, and of course we're going to use a controller, and specifically a PI controller, which is very common in power converters. Rather than P control is not sufficient, proportional control, because you would have a large steady state error when your steady state operation. You won't really get, you can get close to, but you won't get that exact voltage which you want. That's why you need the integral part of it, which removes steady state error. D control, if you say PID controllers are generally common, but derivative control is generally for sudden changes, and generally these load changes and output voltage changes are not very fast, so they are over a period of time, so you don't really need derivative control here. So just a PI controller should be fine. So you need to choose the gain values, KP and KI values, and this again, there is a lot of control theory behind this, board plots, all of that. You have to look at the phase margins, magnitude response, and all of that, looking at the crossover frequencies. There are many such words, but yeah, or you could just use trial and error. That's a basic way to start it. But yeah, these are the values which, after a lot of experimentation, these are the values which I'm satisfied with as of now. KP is around 0.01 and KI is 5. So this is higher because I want to eliminate the steady state error, which if I keep this low, there will be a large steady state error. So we have that. And one thing that they do in PI controllers generally is clamping, which is basically proportional part of your controller, right? If I just go down to my code here, my main while code, you measure your voltage, right? And for that you basically have a timer. I've set up a timer here. Every 10, it's a 10 kilohertz timer, which means it generates an interrupt every 10 kilohertz and samples the voltage. And after the ADC, again I've set it up with the interrupt, so after the it finishes the measuring, because it's not instant, there's a sample and hold capacitor inside which has to charge, then it takes the value. So you need to wait for a while, that's why you have these interrupts. So after it finally completes its measurement, you can take the value. And generally in this is ISR, right, interrupt service routine, you don't want to keep this very big, you want to come out of this as soon as possible, otherwise it's gonna be stuck here. So that defeats the whole point of interrupt service routine. So what they do is generally set a flag after something has happened and you want to change something, you set a flag and you can handle it in the main function, so inside the while one loop. So that's exactly what I'm doing here. So once the conversion is done, basically it stores the voltage. And yeah, that the preprocessor directive which I showed you, it's going to get the actual, this is going to be a digital value, this will be a float value in yeah, decimals. So after you get that, you need to measure the error, so that's where the entire PI controller of it starts. And if I just show you the simulation here, maybe it will make it better. This software, I don't think I've shown it before, it's PSIM, Power Sim. This is very famous in power electronics for simulations. Compared, I've used MATLAB, and Simulink is also nice, but this is optimized for switching circuits. So I have the boost converter set up here, and after you basically measure your output voltage, this is your output voltage, you minus it from your reference, what you want, this is your set point. So let's say I want 24 volts. So it's gonna find the error, this is a summer block, and pass it through the PI controller, where you again fill in all the values. And this is going to be how much corrective action is required, the output of the PI controller. And then you just compare it with the carrier, the same thing, in order to generate PWM. And the switching frequency which I'm going to be using is 100 kilohertz, which is a common one. So yeah, the sawtooth is generated at 100 kilohertz. You compare it in this comparator and you generate the PWM. So, and that goes to your boost switch, which decides how much time to charge the inductor and then discharge it. So if we just run this simulation, you can see here, after I run this, yeah, we can see two things here. You can see the duty cycle and the gate waveform and the output voltage. First I'll just show you the output voltage. You can see here there's a rise time, of course same as any second order system. And if I just zoom in here, you can see that at steady state we have almost exactly, since the simulation it's very exact, you can see here with the triangular ripple, because of course there's going to be a ripple voltage, you have 24 volts. And if I just add another screen here, you can show you the gate waveform too. You can see here we have the PWM, and if I use a measure function or something, you can probably see the duty cycle, but it's somewhat close to 70%, 69%, something like that. So you can see in simulation, once it works, then you basically move to the hardware. You always want to do a simulation first, because if it doesn't work in simulation, it most probably won't work in hardware. And in simulation, max to max you'll get an error, nothing big will happen. In hardware, things can blow up and stuff. So yeah, always do simulation first. And yeah, now that I've shown you the circuit, going back to the code, what they do is after calculating the error, your KP acts on the immediate error, that's why you have KP into error, whereas the KI reacts to the error over time. So you basically just keep adding this over time. Yeah, that's the integral error. And what they do is generally in the start the error is very big, right? So your this term would become very large, and then at steady state this thing wouldn't reduce because this variable has become very big. So what they do is in the start, they, in order to control this, they use something called clamping, which means you limit how much the integral, like the basically how much error the integral can act on, so that over the time this should come to zero, right? You don't want it to permanently saturate, then you'll get a permanent high duty cycle, you'll never achieve your voltage. That's why I've clamped it. So basically if your thing goes above a max, you clamp it. If it goes below also, again, if there's a negative error, you will again never reach. So that also a minimum. This is generally 0. So yeah, this is 0. After that, again, you want to clamp the duty, and this is very important in a boost converter. When I did the buck converter, I think I did something like a 95% or something, but it's not really needed basically, because in your buck converter, if you do 100% duty cycle, you will just get your input voltage, since it's a step down converter. But in a boost converter, since you're stepping up voltage, essentially if you make your duty cycle very high, let's say something like 90%, which means 90% of the time your inductor is just charging through this switch, through this path, and only for 10% it's actually discharging. So that's actually very dangerous, because the inductor, it, after all, it's reacts to changes in current, right? LDI by dt, the voltage across an inductor. So in steady state, it can actually start, acting like a low value resistor, you could say, basically a short circuit. So like let's say in a DC circuit, if you use an inductor, it essentially acts as a short, right? In the same way, so a very large current would basically flow through this and even destroy your entire circuit. So you need to limit, definitely you need to limit the duty in a boost converter, and generally they limit it to something like 80-85%. But for safe case, I've done, here you can see duty max 0.75, so I've limited it to 75%. So if the controller tries to demand a duty greater than that, it should be clamped. So that's exactly what it does. And if you don't include this line in the start, definitely your duty is going to become 100%, and within microseconds your MOSFET can just blow up, and yeah, disastrous things will happen. So definitely look at this. And after that is just multiplying it with the, this is your final duty, multiply it with the actual reload register, and yeah, write it to the capture control register, and that should generate your PWM on your pin. So yeah, that's the entire code. Not very tough, but yeah, need just getting understanding it takes a bit of time, but yeah, it should be good. So now that we've got the code out of the way, let's go to the actual hardware circuit, which is the important part. And yeah, we're going to be starting with the 24 volt reference, right? So let me just switch over to the hardware. Okay, so moving to the hardware circuit, this is the microcontroller, and especially the board itself, actually, not the raw microcontroller. This is the Nucleo F446 board, same as our MSP board. So yeah, there's the pins which are going, and this is the driver, the same IR2110 driver, which is nice. It can drive both high and low side, but now we're just going to be using for low side. And there's the power circuit. And yeah, again, 100 kilohertz on a breadboard is probably a bad idea, but for just showing you how the power converter works, again, there are a lot of limitations, but yeah, it should be fine for now, just for showing. We have the MOSFET, the gating resistor, that's the diode, and our capacitor. And again, as I said, we need the resistor divider, right? So we have a 10k and 1k to scale down the voltage. And after that, it's just a low pass filter of 1k and 100 nanofarad to just remove all the switching ripple. And yeah, that goes to our ADC pin over here in the microcontroller. And we have the oscilloscope setup here. I using this small one today, since we just want to look at getting waveforms. This should be enough. And I have a upgrade since last time. For the closed loop buck, right, I just used one power supply for the driver as well as the power stage, and generally they avoid that because you want the driver voltage to stay constant. You don't want it to be affected by how much the load is drawing on the power stage. So the power supply today will be used for the power stage, actual the boost converter, and the driver will get its voltage from this wall brick here, common one. Get it for cheap, 400-500 rupees. Again, it gives fixed 12 volts, so this should be good for that. And our inductor here, 330 microhenry, toroidal type, and capacitor 20 microfarad, 10 in parallel microfarad. And the load here, since of course there's a breadboard, you can't put this power resistor inside this. It will probably destroy the contacts or not even go in. So yeah, we have this here, 100 ohm. So this should draw a decent amount of power at 24 and 30 volts. So yeah, 10 watt rated. Don't use those small puny ones, they'll just burn up immediately. So yeah, through the crocodile cable. It's connected across the load. So the code is already flashed. I have it connected here. The only thing left is turning on this, so I'll do that. So once I turn on, you can see here our gating waveform. We have at 100 kilohertz roughly 56% duty cycle, and main thing you can see, it's stable. So again, once you do a lot of closed loop control PI controllers, you'll see how you deal with oscillations, steady state error and all of that. So you can see here this is relatively stable, there isn't any oscillation. And on our output voltage, you can see here we have 23.8 volts. Again, there's a tiny bit of steady state, but see, as you can see live, it generally corrects it over time. But yeah, we have about within 200 millivolt, which should be close enough. And yeah, that's demonstrating our 24 volt, how through the ADC we're measuring and the PI controller is working. And just to demonstrate how it can dynamically change its duty cycle, I have another load here, another 100 ohm. So I'm just going to be touching this and putting it in parallel with the current 100 ohm, which would basically bring down the load to 50 ohm and draw double the current. And let's see how it handles that. Normally if you had a open loop controller, that would just bring your voltage down immediately, even below 20 volts, because it can't handle at the same duty cycle, it can't handle that much load. So now since we have a closed loop, I'll just touch this here, and you can see our voltage drops to 22, which is still within roughly 2 volts of our actual 24 volts. Of course you can tune this better, and you can see here the duty cycle, which was 56%, yeah, it increased sort of like 59. And if I remove this again, it goes back to 23. So you can see how it adjusted, and we're back to the original duty cycle here. And that's how the closed loop is working. And just to show you how we can use different voltages, not necessary that only 24 volts. Again, depending on your application, you may want any voltage, right? So I'll just turn this power stage off here. We're back to 0. And in this, since I've written the code in such a way that you can immediately change it, let's go and try out 30 volts. And I'm not going to be changing anything else. The PI values are all going to remain the same, and I'll just flash the code here. So you can see it's flashing, and yeah, the LED is blinking. That shows that it's flashing. And once it's done, it will stop blinking. And yes, the code is done flashing. I'll turn this on again, and you can see again now we have 29.65. again, there's a bit of steady state, but nevertheless you could see how immediate just one line change in the code magically brought our output voltage to what we wanted. And again, just trying out the same load change, now you can see the duty cycle, it's 67%, because of course you want more voltage, so more duty cycle. And if I just put this 100 ohm again in parallel with it, you can see our voltage drops to just 1 volt below 27.75, and it's sort of keeping it at that. And yeah, the duty cycle has increased too. It's getting a bit hot, so I just had to pull my hand off it, and this is also blurry. But yeah, let me just 1 second connect it again, and you can see it's roughly going to 75%, which is the max duty cycle. And yeah, that's showing you that it's remaining within bounds, definitely. That, yeah, if I connect it, so yeah, that's demonstrating the whole closed loop part of it. And just to show you that how right now you saw that it went to almost peak, right, 75% duty cycle, but we have clamped it, we're not allowing it to go above that, right? So if I just increase this a bit, let's try and maybe go to 80%, we can clamp it, not more than that. I'll flash this new code again, and you will see that we'll go even closer to our set point. Again, at 50 ohm load we can get closer to 30 volts, because we are letting it get more duty cycle. So now that I've flashed this again, I'll switch the power stage on, and same as before, we have 29.7 volts. But now if I again connect the 50 ohm, you can see, yeah, now we're above 28 point, we have roughly 28.08, since we're allowing it to pump more current. And yeah, the duty cycle also of course went to almost 80%. And yeah, that's the whole closed loop boost converter, sorry. And yeah, this is very important because now, as I said, my upcoming videos, I will probably look at an inverter or something. And of course, a new one, I'm looking at power factor correction, PFCs, which are AC to DC rectifiers basically, but in a way you could say controlled, not in the sense of a SCR control, but there's active rectification going on. So yeah, stay tuned for newer ones. And this is going to be a building block for PFCs. And yeah, I hope you liked the whole video. It may have been a bit long, but I had a lot to cover, right from which microcontroller, just basic control theory, the actual embedded code, power conversion, all of that. So yeah, thank you for if you reached till here watching the entire thing. And I'll be back soon with more power converters and again analog, of course, electronics. And yeah, thank you for watching.